So if we want to start talking about extending our knowledge of trigonometry out beyond um, right triangles, right? Because not every situation in real life is a right triangle. Sometimes we need to look at acute triangles or obtuse triangles. So this is where things like the law of sines and the law of cosines come into play. So the law of sines is defined like this. If I have a triangle ABC, just like I have in the picture, with lengths A, B, and C, then either of these two proportions or identities are true. So sine A over A is equal to sine B over B is equal to sine C over C. Or you can look at the reciprocal, whichever one is easier for you. I prefer the one on the top. Our book prefers the one on the bottom. Either is fine. All this is saying is that the ratio of the sine of an angle to its opposite side are equal for all three sides. So this is the first way that we start to expand our knowledge of trigonometry to non-right triangles. We use this in two cases. We use this if we're given two angles in one side, which would be my AAS case, right? Angle side. Or if we're given two sides and the non-included angle, which would be SSA. So this notation is important. The order matters here to say that it's the two sides given, but the angle is not between. Non-included angle. Right, the included angle would make it SAS. This SSA case I'm going to come back to later because it's actually a very specific or important case in trig. But if I wanted to start using my law of sines with an example, I would look right here. So here's my angle side case where I have two angles, A and C, and one side, 10 centimeters, little a. If I want to think about attacking this triangle, learning how to solve these angles, I want to do this as efficiently as possible. And the most efficient way to start is to find the third angle. I should find the third angle, and I do that by knowing that the sum of the angles in a triangle add up to 180. So 31 and 44 is 75, plus angle B tells me that B is 105 degrees. So here's kind of like part one of my solution. I like to mark them in. You don't have to, but I kind of like to mark in the information as I get it, just as the visual. The visual really helps me. Now I want to use my law of sines to find my side lengths. So I want to find B and C, and I can do that by using the law of sines. When I use the law of sines, I think it's important to set up half of the equality with only given information because of things like rounding error. So I probably, once I get like a little b or a little c, wouldn't use it later. I'm going to kind of anchor my work with this sine A over A because I'm given both of those parts. So we'll start by solving for little b, so sine B over B. So sine A is 31, sine of 31 over little a is 10. Sine of 105 over little b, whatever it is, just use your calculator. I can rearrange this. So I would multiply both sides by 10. Sorry, I would multiply by both sides by, why am I looking at this wrong? I'd cross multiply, excuse me. I would cross multiply, and then I would divide, and I would get 18.75 centimeters. So you're going to cross multiply, and then you wind up dividing by sine 31. I'm going to do the same thing for sine C. So for C, so sine 31 over 10, sine 44 over whatever C is, same thing, cross multiply, and I'm going to get 13.49 centimeters. If I left more room for myself, I'd kind of show that rearrangement out. but I would hope by now that you know how to cross multiply and solve. So that's all I'm really doing. And here are my final two answers, by the way, just to keep consistent and highlight these. And if I want to mark them in, I can, right? So B is approximately 18.75 centimeters, and C is approximately 13.49 centimeters. And my triangle is solved. I've got all three sides, all three angles. So I said I wanted to come back to this SSA case, because when I'm given two sides and an angle, particularly when it's an angle that that's not included, then my triangle can actually be drawn in two ways. So I'm given two sides and the angle that's not included. So I have essentially two sides and the angle opposite one of them. So IB doesn't ever go into detail about when SSA is ambiguous and when it's not. For now, for IB, just assume that SSA is always ambiguous. I can draw this triangle two ways. Because of the information I'm given, I can draw this triangle by the way I have it here, or I can take it and swing this side A actually in. So I still have A, B, C, C, A, B. And I've still preserved the given information. But I can actually draw it two different ways. And since we don't know which triangle to consider, we need to consider both. If we ever come to a point where we never know which one to choose, which one to work with, you have to work with both. So here's my example. And this time I've chosen to kind of use a little more the IB notation where I'm listing sides by their segments, and I have this kind of new looking angle notation that maybe we're not as familiar with. But I can take this information and draw it in two different ways. So here is my first case, sort of, there you go, A, B, C, where I know that the length of AB is 10, the length of BC is 7, and the length of CAB is 30. Well, I could also take this case and draw it so that I swing that 7-unit leg inside, and I still have a 30-degree angle at A. So if I draw it this way, I mean, I still have 10, 7, and 30. I have to consider both. So if we go about solving this like normal, if I look at my case 1 first and I were to solve this, I would start with my law of sines. It's probably logical to start with my my angle C. So I would say sine 30 over 7 is sine C over 10. And I would just multiply by 10. So I know that sine C is going to be 10 sine 30 over 7. And if I use my inverse trig functions, I get an angle of approximately 45.6 degrees. So again, I'm just going to mark that in just to keep track. 0.6 degrees. Well, then my third angle is just adding up the three angles, excuse me. So by doing that, I get that B is approximately 104.4 degrees. I'm going to mark that in. And then I can use the law of sines one more time to find little b, to find side B. Sine B over B. Right, so I'd say sine 30 over 7 is sine 104.4 over whatever B is. And by cross multiplying, I'm going to get 7 sine 104.4 divided by sine 30. I get b approximately equal to 13.56. And this is one way to solve this triangle, but I can, or if you remember, I can draw this a different way. I could draw this another way. And I can actually save myself a lot of time, because what's going to happen, what I have to do is you cannot use the calculator to find this angle B. Sorry, angle C. I guess IB would call it ACB. They'll always, if you use your calculator, it'll always spit out the acute case. But there's a trick. If we consider this triangle as having still kind of been like written into my other case, then here's how this is going to work. All you need to know is that this new angle C, so I'll call it like C new, actually I'll call it C2 for angle C in case 2, is just 180 minus angle C from case 1. This comes from the fact that if I actually draw the triangle out like this, where I put it inside my other case, my dotted line triangle is an is an isosceles triangle. So these angles are the same. This is a straight line, so 180 minus C gives me my obtuse case. So my new angle C is 180 minus 45.6. So my new angle C is 134.4. And now I can use all of the things I need to know. So I can find B. So my new angle B I'm going to follow the same process. 180 minus the sum of the angles I know gives me, whoops, I should say implies, because that's logically the way I'm working. So B equals 15.6. And then I can use my law of sines, right? I can say sine of 30 over 7 is sine of 15.6 over little b. I can cross multiply again to get my angle B, sorry, my side length B, which is 3.76. So you have to be careful with your ambiguous case, your SSA cases, because you have to consider both cases of how I could possibly draw the triangle. So that's law of sines. If I look at law of cosines, you should notice that part of this is going to look very familiar, I hope. So if I have a triangle ABC, it's got side lengths little a, little b, little c, just like I have in my diagram. I could write this out 3 different ways. I could say that a squared equals b squared plus c squared minus 2bc cosine a. And then from this, it follows that I could actually rewrite this for any ordering of my sides and angles. So I'm just going to do that right now. But you should notice a couple things. You should probably notice, or you might have noticed that, whoops, that this looks like the Pythagorean theorem. And you might notice that, let me pick a different color, there's kind of this mirroring, right? I've got whatever I have here, I have its angle out here. Whatever sides I'm squaring inside, I'm also including here. So that mirroring trick is something that I use to remember the law of cosines. I do think it is on your formula sheet though, so you shouldn't have to memorize it. So when are we going to use this? We're going to use this in 2 cases. If we're given all 3 sides, which would be my SSS case, and if we're given 2 sides and the included angle, included angle, that would be SAS. The trick with law of cosines, you only want to use it once. So you want to use the law of cosines once, and then use the law of sines after that. So let's look at a couple examples. Here's my first case where I'm given all three sides. So let's find one angle. So actually, I'll keep the same color. So find one angle. We're going to find angle A. So we're going to find this one. So 4 squared, A squared equals B squared plus C squared minus 2B C cosine A. So let's simplify this. 13 minus 12 cosine A. Just as a warning, you cannot combine the 13 and the 12. Use your order of operations. Right, the 12 and the cosine A are being multiplied, so you can't do that. So I'm going to subtract 13, divide by negative 12. So I get negative 0.25 equals cosine A, which tells me that A is 104.48 degrees. Well, now, since we have an angle and its opposite side, I can just use the law of cosines. Sorry, the law of sines. Use the law of sines. It's easier. So we can do sine B over 2 equals sine 104.48 over 4. Do some cross multiplying. Actually, we don't really need to cross multiply. We can just multiply by 2. So I'll take sine 104.48 divided by 4 times 2. So here's my sine B, and of course I can use my inverse sine, my arc sine, to find the angle, and I get 28.95. Of course, the last step is all the angles must add up to 180, so you can just add these together. Subtract from 180, and I get C equal to 46.57. So that's kind of the flow. That's the whole process. That's the way to go. Use the law of cosines only once. Use the law of sines from there. Realistically, it doesn't matter if you keep using the law of cosines, but it is a little bit longer, I think, and you should always work as efficiently as possible. So let's see one more case where now I'm looking for the side first. And same thing, we want to work toward the law of sines as best as we can. So the best way to do that would be to find the missing side first. We always want to work as efficiently as possible. So b squared equals the sum of the squares of the other two sides, so that'd be a squared plus c squared, minus 2 times the product of those sides, cosine of whatever that angle is opposite the side I'm looking for. So if I put it all together, fortunately I have it right here, I get 2392.74, and solving for b, 48.92. You might be thinking, well, what about the negative, right? Plus or minus, because I had to take the square root. We can't, for all intents and purposes, we cannot have a negative length, right? Try to measure me out negative 2 feet and you can't do it. So we're just going to concern ourselves with the positive case here. All right, well, this is great. I have now a side and its opposite angle, or an angle and its opposite side. So I can use the law of cosines, or I'm done with the law of cosines, and I'm going to use the law of sines from here. So sine 25 over my answer here. It's not squared. Equals, we'll do a first, but it doesn't really matter. So using my work again, doing the same process as before. Take 66 times sine 25 divided by 48.92. 570. Take my inverse sine, and I get an angle of 34.76 degrees. And of course my side C, my angle C rather, is the missing piece in the sum up to 180. So we're going to follow that same process to get that my missing angle C is 120.23 degrees. So that's law of sines, law of cosines in a nutshell. Normally, I would spend almost a full semester on all the material up to this point, but the book kind of wants us to just boil it down and teach it in a nutshell. So that's law of sines and law of cosines. There's one application of this, of the our law of sines specifically. There really isn't one for law of cosines. But to find the area of a triangle, so we know from before that the area of a triangle is 1/2 base times height. Well, there's no defined height given here. We know that the height would probably be this right here. And our angle measure is theta. Well, if we know the angle A, or really theta, I suppose. We'll call it A. If we know the measure of angle A, then sine of A is, well, opposite over hypotenuse, right? H over C. If I look at my area of a triangle formula, I need to know the height. So we can make a substitution here, right? So this would mean that H is C sine A. So therefore my area of a triangle becomes 1/2 BC sine A. It follows that I could actually do this for any combination in this way, depending on the information I'm given. As long as what you might notice, and my trick to remember it, all 3 letters are represented once in the formula. Again, this is something that's probably in your formula sheet, and so you wouldn't really need to remember per se or memorize per se, but I do find it helpful to remember that all 3 letters are represented once. I have BC sine A, I have AC sine B, and AB sine C. Let's practice with a simpler example first before I give you something kind of more IB style. So if I want to find the area of this triangle, I have exactly what I need. I've got the 2 sides and the angle between them. So this is 1/2 BC sine A. 1/2 7 times 12 sine 34. So if I put this all together, I get an area of 23.49 whatever square units I have. That's putting the formula in action. IB wouldn't make it this easy for you. They're going to give you something like this. Find the area of the quadrilateral ABCD. Well, what we notice is I can turn this quadrilateral into 2 triangles by drawing a segment BD. It would help if I knew the length of BD. And it turns out, if I'm looking at this triangle, that it happens to be the hypotenuse of my lower triangle. For all intents and purposes, I'm going to call this triangle 1 and triangle 2. So if I look at the area of triangle, the length of BD, I'm going to deal with triangle 1 and just use my Pythagorean theorem, right? 5 squared plus 12 squared equals the length of BD squared. And BD, that means would be 13, right? BD squared is 169, so BD is 13. So let me write that in. Let me pick a different color so it sticks out here. I'll use blue. All my side lengths are in blue. BD is 13, which is great. This is helpful, but I need more, right? If I need to find these areas, if I start considering my area formulas, area of triangle 1 is going to be 1/2 base height, which fortunately for me, I have a defined height, right? Because this is a right triangle. So this is just 1/2 5 times 12. 5 times 12 is 60, so the area here is 30. If I consider my area 2 of triangle 2, 1/2, well, I know the two side lengths, 13 times 18, but I don't know the sine of angle, well, I guess it's angle DBC. I don't know this piece yet, but I have enough information to do it. If I can figure out a way to get this piece, then that piece plus DBC is 120. And I do have a way, because if I look at my triangle 1, I have an opposite side and an adjacent side, and I can use tangent then to find my angle. This is where IB gets really all about applying the knowledge you know, right, and not just blindly going through it. I get about 22.6 degrees. Well, that tells me then that DBC is 120 minus 22.6. And I get 97.3 or 97.4 degrees. So my calculation just becomes 1/2 times whatever 13 times 18 is, 234, sine 97.4 degrees. I get an area of triangle 2 to be 116.02. So my total area is just the sum is 146.02. Always include your units, so centimeters squared.